Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, IAC. Today's talk is by Professor Veeraruna Kavitha, and she will be speaking on new results in branching processes using stochastic approximation techniques. Professor Kavitha is currently an associate professor at Industrial Engineering and Operations Research, IIT Bombay. She received her PhD degree from Indian Institute of Science, Bangalore. She was an NBHM postdoctoral fellow at Tata Institute of Fundamental Research, Bangalore during 2007 to 2008. Between 2008 to 2011, she was a postdoctoral researcher with Maestro INRIA, Sofia Antipolis, France, and LIA, University of Avignon, France. Her research interests span stochastic processes, performance analysis, game theory, optimal control and optimization, Markov decision processes, and wireless networks. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Kavitha directly. Over to you, Professor Kavitha.
Yeah, thank you, and thanks for the invitation. And yeah, just a second. Yeah. Okay, so like I know the talk is little bit maybe misaligned with the theme of the thing, but there is a lot of connection, and even though the title may be little misleading, I would like to say that this is not just about the branching processes, but it is also about the online social networks and application of these results in analysis of content propagation in online social networks, etc. So that way it is going to suit the theme. So let me, before I move on, like, so the title is about new results in branching processes using stochastic approximation techniques. And this work is mainly with Khushbu Agarwal. She's my PhD student. And yeah, I do have some other pieces of work which I might discuss briefly. So the others are also involved in it. Okay, directly on to the outline of the talk. So as I said, like, this is about new results in the branching processes. So the first thing would be to, of course, be to giving some introduction to the two. So mainly I would be covering two type branching processes, and two type branching processes. And the main features of this work is total population dependency. This is the main feature which we are adding to the work. And then we will also talk about this limit proportions. And so these results are, I mean, I'm going to introduce here, and then I will also get the results here. And they're going to be applied in branching process with attack, and of course, another one which we called it as proportion dependent branching processes. And then this is the main thing which would be of interest probably to this audience, right? And if time permits, I would also like to talk another related item which is also used in content propagation. Okay, so most of these branching processes are used for explaining or analyzing or studying the content propagation, various aspects of the content propagation. Okay, so I will be starting with describing a very simple branching process, and this is continuous time variant. So basically what is happening here, it is a stochastic process which is used to model the population dynamics. So for example, if I take the most simple model in this category, then every individual lives for some random amount of lifetime, produces some random number of offsprings, and it dies. So the population before the death gets subtracted by 1 because the individual dies, and you have new offsprings. So that's how the population after the death looks like. Okay, so this is what this is in the most simplistic model of the branching process in continuous time. There is another variant called discrete time. I would not be discussing about it. It is generation wise and iterations are considered. So let us instead focus on the continuous time branching processes. So when you look at branching processes, these are widely studied objects, and there are many variants of it. For example, single type or multi-type. So this, what I have described, is the single type branching process. Or I already mentioned about discrete and continuous time. In discrete time, all the entire population belonging to one generation dies together, gives birth to a new generation, while we are going to consider more realistic and more interesting continuous time branching processes. Of course, there can be decomposable, irreducible branching processes. Basically, decomposable are ones in which a type of branching, a type of the population can survive without the other, while irreducible is, maybe many of you have guessed. So there are many varieties or types of population. Either all of them survive or they perish together. While in decomposable, some types can survive independently of the other types. And then also the propagation or this offsprings can depend upon the population, or it can be independent. That leads to another category of branching processes. And then the next one is about Markov or age dependent death times. So we already talked about this death time. So it could be basically, the death time could be either Markovian, that is a memoryless death time, or it could be age dependent. And then comes very important category, which is this. So here you have supercritical and subcritical. Basically, this is nothing but expected value of, for example, in this simple model, if the expected number of offsprings is greater than 1, then there is a positive probability that this process explodes. Explodes means it increases exponentially fast with time. Okay, and this happens with positive probability, with probability greater than 0. And when you consider subcritical, in this case, your expected value of xi is less than 1, and it is critical, also the same kind of comments are true, then the population gets extinct with probability 1. So these are all the various varieties of branching processes. Of course, some of the key questions which you might have understood from my description so far is that what is the probability that the population gets extinct? What is the probability? What is this? The probability that xp is equal to 0. Because if it gets extinct, 0 is absorbing state. 0 is absorbing. Okay. So for some t, this is the extinction probability. This is equal to 1 if it was subcritical, and this is less than 1, and if it is supercritical. So we would like to know what is the extinction probability. And then one very important thing is that, maybe I can use the space here. When population survives, then in branching processes, most of the branching processes, the population is going to explode. So we would like to know the growth process. So this is as time progresses, xt, right? We would like to know the growth process. How does it increase? Okay, so I've told you that it is exponentially. So this is true in some of the branching processes. So this is about the growth pattern. So these are all the agenda that we are going to discuss on these aspects today. Okay, so now my focus is not on single branching process as I showed you in the previous slide, but we would like to consider multi-type branching process. And here the relevant question is, let's say there is xt, which is one type of population, right? Li, this is the number of the population size of one type of population at time t, and this is the proportion. So a very important relevant question is, what is the limit proportion? So what is the limit of this? Right? So we would like to know this. And this question is relatively less discussed in the literature. Okay. So basically this is the proportion of current live population size of one of the types, and we are interested in time-asymptotic population, right? Proportion, sorry. And why do we want this? Why? Okay. So there are many applications in which this is going to be important. For example, if you look at this Jager's work, they are talking about limit proportions of the normal cells in a tumor patient in comparison to the tumor cells, right? And similar questions were asked in this relatively recent paper, but this is as initial population changes, right? And then there are many others who have got theoretical studies for various other applications like online social networks or something else, okay? And then, so recently we have applied these we required answers to these kind of questions in two different applications. One is where, so in one case, we are talking about proportion of copies of content of one provider against the other. In the other case, we are talking about fake tags as opposed to real tags. We will discuss more. Okay, so that's what I told you, like we are talking about, let us talk a little more about these proportions. Let's consider viral competing markets. What is this? There are two types of content providers. There are two content providers, say X content provider and a Y content provider. They want to advertise their own content. Okay, so now this is one user and this is another user. This user received only the X post, and it will only have to make a decision whether it likes the post or not. If it likes, it will share it to many other people, and this continues. Now this is another user who has received both the posts, both Y as well as X post. Okay, and then it will have to think about whether it likes to share Y post, X post, or which is more interesting. So in this particular instance, it preferred the Y post. Y post is better, therefore it shares the Y post. So for example, this user received again both the posts, and it might think that X post is better. So there is competition between the two posts when they are advertising or when they're talking about or describing the similar kind of content. Okay, so in some sense, we can say that Y post is attacking the X post, because if you look at this example, initially X was shared because it is down the timeline, and then Y post was shared. If Y post was not shared, probably the user has seen only the X post, it would have shared the X post, but it lost its opportunity to Y post. So there is something called attacks, which is going to be an important aspect in our discussions. And then another very important aspect here is total population. These shares depend upon the total population, in the sense the total number of shares of this post already, because think about a recipient who has already received this post. The second time the person receives the post, that person would not be interested in the post anymore. So we have some kind of dependency on total population. Okay. And then another application of limit proportions. Okay. So this is about controlling the fake tag, fake news propagation. So here, I'll get into more details later. Basically, it is about, we ask the users to tag it as real or false or fake. So for example, this is a real tag and this is the fake tag, right? And based on the number of people that have given fake tag, fraction of people, the control mechanism is designed here. So this is another application where limit proportions are important. Okay, so now that probably we motivated the reason for this exhaustive study of limit proportions, let's go through the actual objective of our study. So as I already said, we are looking at continuous time two-type branching processes, and we are considering just two types of population. And we are considering Markov branching processes. So therefore, the lifetime is exponentially distributed. That means every individual lives for a time which is given by exponentially distributed random variable, and hence is memoryless. And that's why these are Markov branching processes. And then we denote the current population, the population which is alive right now, by these symbols, while the total population, which includes alive plus dead, by these symbols A. And the most important feature of our work is that this offsprings, which we have seen, Xi, in the first slide, right? This is nothing but this, right? These offsprings can depend upon not just the current population as usually considered in the some of the literature or the limited literature. It can also depend on the total population. And the objective is twofold. One is to get limit proportion. Another one is to get deterministic trajectories to study certain normalized trajectories. Okay. So now moving on to the literature survey, like there are variety of work in this area I have already mentioned. So a lot of them, like for example, irreducible branching process or prey predator branching process, and then decomposable branching processes. A lot of these things are there, and but all of them have certain limitations, like for example, they do not consider population dependency, or they do not consider proportion dependent. So similarly, there are more pieces of work like age dependent branching processes, and then there are proportion dependent branching processes which we ourselves studied, but it was about a particular case. So the work that I'm going to discuss today is going to extend all these pieces of work, okay, in some way or the other. Okay, so let us get into more details about the problem. So as I mentioned already, we have two types. And so this represents the state of the system. And this is a continuous time jump process, Markov jump process. Okay, and it is given by this four tuple: current population of X type, current population of Y type, the total population of X type, and total population of Y type. Okay, and then we have the next ingredients, which are nothing but the offsprings, which are dependent on total and the current population produced by an I-type parent. And these offsprings are integer valued. And so, as I said, we are extending our work to include negative valued offsprings because we are considering attack. So that's an extra feature here. And of course, there are some assumptions like we have conditional integrability and the offsprings are greater than or equal to 0, all these things. But what is more important for us is that this piece of work, the first piece of work that I'm going to talk about, is regarding true supercritical regime. Means the expected number of offsprings is greater than 1 for all population sizes. So such processes have chances to grow, explode as time progresses. They can explode as time progresses with positive probability. Okay, so anybody wants to ask me some question, you can ask me before I move further. Any questions so far? Okay. So let us look at the dynamics of the population. So as I already said, that we have self-offsprings. So let's say X type parent dies. So there is a death. So this accounts for this -1. And it produces some self-offsprings, and then it also produces some cross offsprings. As I already told you, it can be negative. If it is negative, then it will represent the attack. Okay. And another, furthermore, the total population simply increments. It's not going to decrease because we are talking about live as well as dead copies here. Okay. And similar dynamics occurs when there is a Y parent which dies. Okay. So the idea here is to get limit proportions. That's the primary goal. And these are one of the important aspects of this branching processes is transient analysis. Most of you may be aware of Markov processes. In Markov processes, the primary focus is on recurrence, right? Positive recurrence when you have stationary distribution. But these things are not true with branching process. Branching process has an absorbing state, which is 0. The population dies or it explodes. It has majority of the processes, meaning it grows tremendously. So transient analysis is more important for this kind of a Markov process. And when we go for this, when we are studying transient analysis, or when we are looking at a transient process, what would be interesting is, as I already mentioned, growth process or the limit proportions, if you have two types of population involved in that. Okay, so in such cases, it is sufficient to analyze the embedded process, right? Especially for the limit proportions. Embedded chain is what? This is the chain which you observe the system whenever there is a change in the system. And in this case, in this system, the change is due to the death. Okay, so look at the tau n, the time instance at which nth individual dies, right? So then this is the population at that point of time, and at that epoch, immediately after this. And of course, this is the sum population. And another important notation for us is this extinction epoch. So in case the population dies, I told you already that it is an absorbing state and it remains here, and that's the extinction epoch. So as I already told you, either that the process gets absorbed into 0 or it explodes. It is called dichotomy. Okay. Yeah, hello?
Kavitha, one question.
Yes.
What is the meaning of AXN and AYN on the third line?
Yes, this is the total population after nth death due to X type, and this is the total population of Y type.
Okay. Then what's CXN and AXN?
This is the current population. Thanks for the question. C is current, and A is like accumulated population from the beginning, which is the total population.
Okay. Okay, thank you.
Yeah, thanks. Okay, so the methodology. So we are going to use this stochastic approximation based approach, and such an approach is not used to the best of our knowledge in the before this, for the branching, in the context of branching processes. And this approach has given us a lot of advantages and privileges, and we could study a lot of things. So as you see, so our journey is right now towards stochastic approximation based techniques. Okay, so towards that, the dynamics at the transition epoch, as I told, this is the current population. As I already told you, there is a death when X type parent, so -1, but the total population will not decrement, and the Y population can either benefit if it has positive offsprings, or it is attacked if it has got negative. Negative means attack. And appropriately, the total population is adjusted. Now comes the main idea. So we want to come up with a normalized. So as I said, this is transient process. And transient process, you need to study some kind of growth rates or growth trajectories in some sense. So towards that, we have to normalize the process. Normalize means if the process has to be multiplied with some decreasing sequence. For example, something like this. So, and in case it converges to a limit, right, which is less than infinity, that means this represents the growth rate of this exploding process. Okay, so that's the meaning of it. So if we are able to identify something like that, it means we have understood the growth of this transient process. Okay, this is the kind of things which are used in branching literature so far. But we are coming up with a very different way of normalizing. The idea is very simple. You please divide it by n, the number of transition efforts. That's sufficient. And this kind of normalized trajectories can be analyzed using stochastic approximation techniques. Okay. So what is the object we are getting? These are the ratios, which are the ratios of the current population divided by the number of transition efforts. Similarly, ratios of the total population, total sum population is divided by the number of efforts. And this is only of the X population, the ratio corresponding only to the X population of the current, and this is of the total. Okay. And it is sufficient to study these ratios. And this is the proportion, which is an object of our interest. And as I already mentioned, the idea is to use stochastic approximation techniques. And towards this, we can show that these things can be written as written to the stochastic approximation framework. Okay, so let's look at that. So the idea is actually can be explained in a very, very simple way. If we consider the most, yes.
Sorry, I'm still trying to figure out what is the motivation for maintaining the A, because it seems to be the population since the beginning without counting deaths. Is that so?
Yes, A is population since the beginning. Yes, the reason is that we want total population dependency. These offsprings will depend upon total population.
Okay.
That's the big motivation. So like, for example, in content propagation, so the number of people who have received the copies so far, that is given by the total population, not current population. Current population is the, yeah.
Achha, got it. So if somebody has received a copy earlier, that person will also be counted in the A variable.
Yes, correct. Because the persons are seldom interested in the same item again, news item or advertisement or post.
Okay. All right. Thank you.
Yeah, thanks. So the idea I'm going to explain, let us say we have population independent offsprings, right? So that means the total new offsprings, this is X type and Y type produced, right? Let us say it is an IID random variable. It does not depend on phi. It does not depend on phi. Okay, it's the same. Okay, so then if you look at the sum population, the ratio of the sum population, this simply converges to sample mean by strong law of large numbers. This ratio, you divide it by 1 by n. And what is going to happen in the actual branching process? In the actual branching process, if you look at the ratio corresponding to the total population, till extinction time, it will be the same as this phi bar n. After extinction, of course, it will become nu e by n. It's because the process is stagnant after extinction. So only the normalization is increasing. So that means what is going to happen? The simple observation is that in the extinction paths, this ratio is going to converge to 0. And in the survival or viral paths, right, it is converging to m bar. So the analysis is quite simple here, right? Because this is just the strong law of large numbers. Now, this is the idea which we are going to leverage to study much more complicated processes. So to explain that idea, basically the sample mean can be expressed. I think many of you might be knowing it. We can write it as an iterative algorithm or a scheme. Of course, the actual process is much more complicated because it depends upon the type of the parent which dies, which is HK or 1 minus HK when Y type dies, right? And so it's little more complicated, but the idea is already clear here. And so this has got an iterative structure, and therefore you can use stochastic approximation techniques. And another interesting thing is some of you who are working in stochastic approximation techniques know that one of the key aspects is bounding of these iterates. And that's going to come to us very easily due to law of large numbers. strong law of large numbers. Okay, so even though this is the offsprings are time varying, they're population dependent and all this, once you have an upper bound on these offsprings, then I can use strong law of large numbers. Okay, so now, yeah, of course, this is messy thing. I just want to flash this. So this is for total population, current population, current sum population, current population corresponding only to X type, and total population, sum population, X plus Y, and this is only to Y population. Betas are for X, and these are for sum. Okay. But as I already said, all of them can be bounded using this, and which converges to a sum M bar almost surely by strong law of large numbers. Okay. Now, there is another aspect whenever you consider. So, throughout, I would like to tell you this PD is population dependent. Population dependent. Dependent offsprings. The offsprings are population dependent, and P and D is population independent. So, we will be using these short forms. So, whenever you consider this kind of a analysis, population dependent branching processes, the literature assumes that the mean matrix, right, expected number of offsprings, which will be 2 by 2 matrix in this case, converges to a constant. This is the usual assumption made. We are going to allow it to converge, but we have more. We can, our stochastic approximation based scheme approach allows us to consider that it converges to proportion dependent mean matrix. So our M can depend on betas. Beta is the proportion. Okay, so that's the proportion. And of course, these are the usual assumptions which are made in the literature, that as the sum population increases, it converges. So the literature does not consider the dependency on the proportion, but we are considering. And it also talks about the rate of convergence. We have similar kind of assumptions there. But what is more important is, because we are also considering attacks, so our this mean functions can be discontinuous. So this is another thing, those of you who are working in stochastic approximation, you know that dealing with non-smooth dynamics or ODEs is little more complicated. Okay, so as is the case with stochastic approximation techniques, the one of the most famous approach here is ordinary differential equation based method, and this will be the ODE. And okay, this may be a little complicated, but just to see that, you know, this is the death, this represents the death, and these are the additions, and so on. Okay, and in the total population, there is no death. Yeah, as you can say, there is no -1, just to make you comfortable with the ODE. So the important feature of this ODE is that it is autonomous, it is non-smooth, that's the thing, and it depends only on limit mean functions, this one. Okay, limit mean proportions. Primary, because it also depends upon whether the population is extinct or not. Okay, fine. This is the ODE that we have, and the usual kind of theorems that we can have, that it converges. So basically, this is the stochastic iterates or the population at various extinction, the death epochs, and this the corresponding ODE. The difference between the two of them converges to 0 in a finite time scale when they are initialized with the same initial conditions. And then we also have convergence to the attractors, and this is important thing. So this is another new thing in ODE approximations. We are also talking about convergence to repellers. Basically, repellers are the equilibrium points. So if the ODE has an equilibrium point or the critical point, you initialize anywhere close to it, the trajectory diverts away. They are called repellers. And what we see is that these repellers in fact play a lot of role in our analysis. So the result is that the stochastic approximation iterates converge to this with at least this probability. What is this probability P? PB is the probability that you visit a compact set or the repellers infinitely often. So that's the assumption, and with this assumption we have the result. Okay, and then before I proceed towards the other examples of the branching processes, I just would like to tell you that we can analyze. So that was a 4 tuple. This ODE was 4 tuple, but you could just analyze the proportion ODE and you could get all the analysis. The main thing is that if beta star is the repeller or the attractor of the above ODE, H beta star will be the attractor bar repeller of the original ODE. And for that, you need that you are considering viral paths. Of course, in the extinction paths, the ODE has equilibrium point as the 0 vector. Okay, so just to illustrate the accuracy of this stochastic approximation. So this is the ODE trajectory, and this is the real trajectory, the red curve. And we have another ODE, which I did not describe because of lack of time. So we have these approximations, as you can see that they're pretty good. Okay. So the summary so far, any BP, which is either population dependent or population independent, irreducible, decomposable, positive, negative offsprings, whatever happens during transients, but can be analyzed with the same limiting ODE. And that ODE, instead of analyzing the 4-dimensional ODE, it is sufficient to analyze 1-dimensional ODE, which gives you the entire analysis. Okay. So now let's move on to one example, right? So I'm going to talk initially about negative offsprings or the attack. Okay, so the simplest models, which was already analyzed in the literature, is single-sided attack. So here, this particular paper considers population-independent offsprings, population-dependent attacks, and it talks about when there is a possibility of co-survival, right? And when is it that they cannot survive together? These are the kind of things. And yeah, and we can achieve similar kind of analysis. This is a mean matrix corresponding to that. And we can show with our 1-dimensional ODE, when is it that X-type dies? 0 proportion means X-type dies. 1 proportion means Y-type dies. Beta R star, which is strictly less than and greater than 0, implies co-survival. So what is the extra we have? We have beta R star in comparison with the previous analysis. So we know the exact limit proportion in co-survival sample paths. Okay. And further to that, we can also consider the we can also consider the case for population dependent variants, right? What we need is that in the limit, it is this matrix. So this analysis is applicable. Okay, moving on. Let us consider branching process with attack, which has basically double-sided attack. I think, yeah, double-sided attack and acquisition and total population dependency. So basically, again, this is the current population of X-type. Both of them are attacking in this case. In the prey predator, only X-type was attacking. Here, both are attacking. So when X-type wakes, it produces self-offsprings, which is population dependent, and it has acquired Y individuals and has attacked and acquired them. And of course, it dies. So the Y population has a negative offsprings. So this is about attack plus acquisition. Acquisition was also not there in the prey predator model. So this kind of analysis is not available in the literature so far. And so this particular branching process has this kind of an ODE. And this has, of course, if many of you might have identified, we do not have classical solution. In the sense, we do not have continuously differentiable solutions of the ODEs because the right-hand sides are discontinuous. So we have in the extended sense. In the sense, the solution satisfies the ODE only almost surely, with respect to the Lebesgue measure. Okay, so yes, talking about the asymptotic analysis, we have two types of limit mean matrices. Okay, so one of the matrices, here co-survival is possible, here co-survival is not possible. Okay, that is shown here. Only beta star R is possible in the red type. What are these? So X is always attacking, and here Y is also attacking. Either that case, so that means you have double-sided attack, or only X attacks because this is 0. But Y type has more reproduction capacity because this is the expected number of offsprings at the limit of Y type, self offsprings. This is bigger than the self offsprings of X type and the attack, expected number of attacks. In case Y can reproduce much more than the attack plus this, then co-survival is possible. And this, as you see, it is coming from the repeller side. This is the repeller. Okay, if that is not the case, right? Either there is a single type of attack, and of course, X type is more powerful. In that case, co-survival is not possible. No co-survival. So you can also see the attractor is 1, while this is the repeller. Okay, so there is no. I mean, if I had time, I would have explained why these repellers are also here. So repellers. So if in the ODEs, unless you start at the repeller, the trajectory does not converge to the repeller. Okay, but the stochastic iterates, the trajectories can converge to the repellers. So that's I can take it offline because it needs some explanation. Okay, so let's now move on to the application. So the first application is about content propagation over the OSNs or the viral marketings. And here, basically, this is an economic solution. What is that they are doing? They buy some seed users and post their advertisement post over that. And if a user reads it, it can post to many people. And depending upon the interest generated, they share. The number of shares depend on that. For example, this user did not like it, so the user did not share. Okay, and this is where total population dependency comes, which I already told before. So the success of a post is either the post gets extinct in the initial phase, or there will be shares of shares of shares, and the explosion of the copy cycle. That's why it is called viral marketing. Okay. Now, again, there are a lot of approaches to study, but each one is meant for different things. Like, for example, random graphs, they cannot capture explosion. If you take epidemic-based models like susceptible, infected, and recovered models, right? These are more appropriate for word of mouth because they talk about person infecting or sharing till recovery. While on OSNs, typically the people lose interest after sharing the post once. They see the post, share it to some bunch of friends, and then they forget about the post. So this is more apt for word of mouth behavior. Okay. So, and then you have single post propagation in this paper, and we are considering viral competing markets where there is a competition between contents. So let's just dwell into this timeline structures. So the posts are stored in this inverse stack. There is a next type post. Let's see, it is shared. It comes and occupies here. It pushes down the remaining content. Now another new post comes, the X type occupies lower. And then let's say the Y post, which is a competing post, arrives here, right? Now you have the timeline which has these two content which are competing with each other. In the sense, the user might be interested only in one of them, not both. Okay? So when the user arrives here, it either forwards to X post or Y post, as I already told you that. So if it still likes Y post, then attack is not successful, right? So these are the ones. If it likes the X post more, then attack is successful because Y was initially shared, right? So therefore, you will have this propagation, which is exactly like BPA. And so it models the viral markets. Okay. And yeah, I think I'm just kind of running short of time, so I'll have to skip this. But as I already told you that the co-survival, these are the things. This is going to happen, and this case study is with respect to that. And yeah, some numerical examples will show you the co-survival probabilities. And it also confirms the theory that either it is the entire X population is wiped out, or Y population is wiped out, or there is one unique co-survival limit. And so that co-survival limit is also shown in the simulations here. And yes, yeah, I think now I'll very quickly discuss the proportion dependent branching processes. So as I told you that in this case, the mean matrix. So yeah. So the mean matrix is assumed in all the literature that we have seen to be population independent, but we are considering proportion dependent model, which is going to help you because in some of the examples you may not know the proportions, and so you cannot know the limit matrix. Okay, but if you use proportion dependent model, you can derive this limit using some simple fixed point equations. So that's the objective here. We again have some theorems which is going to give you the results here, and then let's move on to the application, the more interesting thing. So let's say there is a news item on your OSM. You don't know whether it is fake or real. Okay? So whenever a user receives, these days we are really bothered with the existence of a lot of fake news items. So we don't know whether the news is fake or real, right? So always there is a lingering question in the mind of every user, and there are a lot of disadvantages and a lot of issues which people have noticed across the globe because of the fake news. Okay? So now recently we have proposed a fake news, a warning mechanism to identify the fake news. So our objective was to identify if it is a fake news without identifying a real news as fake beyond some tolerable limit. That was the idea. Okay, so the question that we had asked ourselves was, can a warning mechanism? So basically the main idea is about collective wisdom. Individual user cannot detect whether the news is fake or news. They have some intrinsic capacity, but an individual single person may not be sufficiently judging the news to be fake or real. But the collective wisdom, right, is it going to help us? And the answer is yes. Okay, so the idea is actually quite simple. Every user, right, every user is going to receive a system generated warning, and its sender will send a tag that it is the news is fake or tag, and the user has some intrinsic thinking capacity. It uses the warning and the tag of the sender and its own capacity to generate fake or real tag again, and this one is consolidated. This and the tags from the other users are consolidated, and the system generates a warning. And this is the mechanism, feedback mechanism, which seems to work very, very well. Okay. So again, yeah, just to summarize, so this is the post with real tag, post with fake tag, and the warning mechanism here depends upon the ratio of fake tags, and that's why we needed proportion dependent branching processes. Okay, so then we can again use the results that we have derived so far, and this is the thing which I was telling you. We could get the limit proportion by solving this kind of a fixed point equation, and we have the theoretical as well as numerical results using SNAP dataset, which shows that 90% of the users can detect the fake news as fake news. If you allow 2% of users to detect real news as fake news. So there was an optimization problem. I'm not getting into the details. So this analysis is using our proportion dependent branching process based result. So probably just, yeah, I think I want to talk about, so far we talked about super branching processes, while here super to subcritical, and that's simply possible only because of total population dependency, because we have a kind of monotonicity. So this is about, as I told you, like when you share a post to a user, like for example, this user is already having a post, another friend is trying to share, the user is simply not interested. So the effective number of forwards decreases and depend on total shares, which is nothing but the total population. Okay. So we can do analysis in a similar manner, and we have got the ODEs for this, and we analyze them. And the important thing is that this is the trajectories. This is the approximation of the trajectories after n forward. And this is all. So the important feature about that super subcritical is that this gets extinct with probability 1, but it explodes before getting extinct. That's the difference. So these branching processes are really new. I've not seen them before, right? And this allow you to capture virality as well as almost sure extinction, which is the realistic feature of the content propagation. So to just show you the idea, so the total shares, sorry, this is the current shares. Current is nothing but unread copies. They explode and then they die, while the total shares or the total copies are going to saturate. Okay, and you can see the ODE approximation is very good, and it allows us to calculate a lot of relevant performance measures like peak shares, lifespan, max rates, etc. And we also have come up with an algorithm which is able to predict the peak shares within some amount of number of forwards. Like for example, it is predicting at this point itself. By then itself, it's pretty close to the peak shares. Okay, the prediction, prediction. So that is about it. And yeah, sorry, I took little more time than what I anticipated. Just quickly conclude that we are considering a general class of population, which includes total population dependency, which is completely a new feature. And we have come up with a new procedure to derive the limit proportions. We have analyzed quite some variants branching process with attack or proportion dependent or total saturation. And we have derived, in the last case, we have derived approximate trajectories, as well as we have also derived this. Yes, thanks. I'm happy to take any questions.
One question.
So
In this, are there any analysis done on the reward-based sharing? Since for each type there is a specific reward.
Yeah, I mean, you can think about it like this warning mechanism. In some sense, you can think it to be reward-based. And yeah, and so another thing that I would like to say here is we are in fact having a next. So yeah, 2-3 comments I have on this. First thing is, if we want reward based, we can easily extend the analysis because the framework is quite general. Any new branching process you want to think of, we can do it. Second thing is, we are indeed coming up with a reward based warning mechanism where we compel the users to participate by giving rewards. So yes, we are also trying to consider. As I said, this approach is quite general.
So one question, Kavitha.
Yes, yes. Yes, please.
So the analysis was done using these transition epochs when,
yes.
When an individual dies.
Right, correct.
Okay. So it was embedded at those epochs. Now, from there, can you also get the proportions at any time, any point in time?
Yes, actually, that's a good question. I believe we can get,
Achha.
but it requires, definitely it requires extension of analysis.
Okay, fine. And the second question that I had is, I think somewhere in the development you used the point that the number of offspring is bounded. Is that so?
Number
In
of
one of
offspring, and not number of offsprings, but the expected number of offsprings is bounded. And we are bounding, so we are having a common random variables to bound the number of offsprings. Almost surely.
Okay, okay. Oh yeah,
You
then I was
can,
confused.
you can probably extend it easily to stochastic dominance.
Hmm.
So we basically need a uniform bound independent of the population sizes. That's all we need.
Okay, great. Thank you.
Yeah, thanks.
Are there any other questions? If there are no more questions, let's end this session. Thank you, Professor Kavitha, for an interesting and informative talk.
Yeah, thanks. Yeah.
As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the web page. Thank you and have a great evening.